We've been scaling our neural network training compute dramatically over the past few years. And today we're barely shy of 10,000 GPUs, which, just to give you some sense, in terms of number of GPU, is more than the top 5 publicly known supercomputers in the world.
And we are not done. We are assembling our first cabinets pretty soon. And we have a whole next generation plan already. We are thinking about 10x more with different aspects that we can do, all the way from silicon to the system again.
Things that I think that are really hard about having a useful humanoid robot is, can it navigate through the world without being explicitly trained? Without explicit, line-by-line instructions.
Tesla Throwback Thursday. Today we're going to go back into the 2021 AI Day from Tesla. Part B, mind you. You missed Part A, you can catch it right about here. Or just wait until the end of the video, it'll be there too. Without further ado, let's get to it.
I'm responsible for the integration of our neural networks in the car and for most of our neural network training and evaluation infrastructure. And so tonight, I'd just like to start by giving you some perspective into the amount of compute that's needed to power this type of data generation factory. To get rid of the dependency on the radar sensor for autopilot, we generated over 10 billion labels across 2.5 million clips. And so to do that, we had to scale our huge offline neural networks and our simulation engine across thousands of GPUs and just a little bit shy of 20,000 CPU cores. On top of that, we also included over 2,000 actual autopilot full self-driving computers in the loop with our simulation engine. And that's our smallest compute cluster. The two main constraints that we're working under here are mostly latency and frame rate. The meat of the problem really is around the AI compiler that we write and extend here within the group that essentially maps the compute operations for my PyTorch model to a set of dedicated and accelerated pieces of hardware. And so, by the way, we're not doing that just on one engine, but across 2 engines on the autopilot computer. And the way we use those engines here at Tesla is such that at any given time, only one of them will actually output control commands to the vehicle, while the other one is used as an extension of compute. But those roles are interchangeable, both at the hardware and software level. We have been scaling our capacity to evaluate our software and neural network dramatically over the past few years. And today, we're running over 1 million evaluations per week on any code change that the team is producing. And those evaluations run on over 3,000 actual full self-driving computers that are hooked up together in a dedicated cluster. We've been scaling our neural network training compute dramatically over the past few years. And today, we're barely shy of 10,000 GPUs, which, just to give you some sense, in terms of number of GPU, is more than the top 5 publicly known supercomputers in the world.
Damn!
But that's not enough, and so I'd like to invite Ganesh to talk about the next steps.
My name is Ganesh, and I lead Project DOJO. As you saw from Milan, there's an insatiable demand for speed as well as capacity for neural network training. And Elon prefetched this, and a few years back, he asked us to design a super fast training computer, and that's how we started Project DOJO. Our goal is to achieve best AI training performance and support all these larger, more complex models that Andre's team is dreaming of, and be power efficient and cost effective at the same time. A distributed compute architecture. After all the training computers out there are distributed computers in one form or the other. Easy to scale the compute. It's very difficult to scale up bandwidth and extremely difficult to reduce latencies. For DOJO, we envisioned a large compute plane filled with very robust compute elements backed with large pool of memory and interconnected with very high bandwidth and low latency fabric and in a 2D mesh format. We wanted to attack this all the way, top to bottom of the stack, and remove any bottlenecks at any of these levels. And let's start this journey in an inside-out fashion, starting with the chip. As I described, chips have compute elements. Our smallest entity of scale is called a training node.
You still with me? I don't know what's going on, but it seems really informative.
Was we picked the farthest distance a signal could traverse in a very high clock cycle. In this case, 2 gigahertz plus. And we drew a box around it. This is the smallest latency that a signal can traverse, 1 cycle at a very high frequency. And then we filled up the box with wires to the brink. This is the highest bandwidth you can feed the box with. And then we added machine learning compute underneath, and then a large pool of SRAM. And last but not the least, a programmable core to control. And this gave us our high-performance training node. It would be our smallest entity of scale, but it packs a big punch. More than 1 teraflop of compute in our smallest entity of scale. Computer architects out here may recognize this. This is a pretty capable architecture as soon as you see this. We call it in order, although the vector and the scalar pipes can go out of order. But for the purists out there, we still call it in order. And even in the physical realm, we made it extremely modular, such that we could start abutting these training nodes in any direction and start forming the compute plane that we envisioned. When we click together 354 of these training nodes, we get our compute array. It's capable of delivering 362 teraflops of machine learning compute. And of course, the high bandwidth fabric that interconnects these. And around this compute array, we surrounded it with high-speed, low-power SerDeses, 576 of them, to enable us to have extreme I/O bandwidth coming out of this chip. If we put all of it together, we get training optimized chip, our D1 chip. This was entirely designed by Tesla team internally, all the way from the architecture to GDS out and package.
GM, Ford, they've got their own chip too, right? Lucid? Rivian? I mean, Tesla's just a car company like them.
This chip is like a GPU-level compute with a CPU-level flexibility and twice the network chip-level I/O bandwidth. If I were to plot the I/O bandwidth on the vertical scale versus teraflops of compute that is available in the state-of-the-art machine learning chips out there, including some of the startups, you can easily see why our design point excels beyond par. 500,000 training nodes together to form our compute plane. This is 1,500 D1 chips seamlessly connected to each other. This is what we call as a training tile. This is the unit of scale for our system. This is a groundbreaking integration of 25 known good D1 dies onto a fan-out wafer process, tightly integrated such that it preserves the bandwidth between them. The maximum bandwidth is preserved there. And in addition, we generated a connector, a high bandwidth, high density connector that preserves the bandwidth coming out of this training tile. It was not easy to design this. There were no tools that existed. All the tools were croaking. Even our compute cluster couldn't handle it. Our engineers came up with different ways of solving this. They created new methods to make this a reality. Now that we had our compute plane tile with high bandwidth IOs, we had to feed it with power. And here, we came up with a new way of feeding power vertically. We created a custom voltage regulator module that could be reflowed directly onto this fan-out wafer. So what we did out here is we got chip, package, and we brought PCB-level technology of reflow onto this fan-out wafer technology. We didn't stop here. We integrated the entire electrical, thermal, and mechanical pieces out here to form our training tile fully integrated, interfacing with a 52-volt DC input. It's unprecedented. This is an amazing piece of engineering. What it is a 9 petaflop training tile. This becomes our unit of scale for our system. And this is real. I can't believe I'm holding 9 petaflops out here. Last week, we got our first functional training tile. And I was told Andre doesn't believe that we could run networks till we could run one of his creations. Andre, this is MinGPT-2 running on DOJO. Do you believe it? Did we stop here? No. We just integrated seamlessly. We broke the cabinet walls. We integrated these tiles seamlessly all the way through, preserving the bandwidth. There's no bandwidth divot out here. There's no bandwidth cliffs. All the tiles are seamlessly connected with the same bandwidth. And with this, we have an exapod. This is 1 exaflop of compute in 10 cabinets. Not just the hardware, the software aspects are so important to ensure scaling. Our compute plane can be subdivided, can be partitioned into units called DOJO processing unit. Our compiler uses multiple techniques to extract parallelism. In addition, our compiler is capable of handling high-level dynamic control flows like loops, if then else, etc. The stack consists of an extension to PyTorch that ensures the same user-level interfaces that ML scientists are used to. So with all this, we integrated in a vertical fashion. We broke the traditional barriers to scaling. And that's how we got modularity up and down the stack to add to new levels of performance. It'll be a fastest AI training computer, 4x the performance at the same cost, 1.3x better performance per watt, that is energy saving, and 5x smaller footprint. This will be DOJO computer. And we are not done. We are assembling our first cabinets pretty soon, and we have a whole next generation plan already. We are thinking about 10x more with different aspects that we can do all the way from silicon to the system again.
They are never done. Every level of Tesla is constantly thinking about the next form of disruption. If you don't disrupt yourself, somebody will be happy to do so. We went from a human dancing on stage to this.
So DOJO is real. The Tesla bot will be real. If you think about what we're doing right now with the cars, Tesla is arguably the world's biggest robotics company because our cars are like semi-sentient robots on wheels. Neural nets, recognizing the world, understanding how to navigate through the world. It kind of makes sense to put that onto a humanoid form. Eliminate dangerous, repetitive, and boring tasks. We're setting it such that it is, at a mechanical level, at a physical level, you can run away from it. I mean, things that I think that are really hard about having a useful humanoid robot is, can it navigate through the world without being explicitly trained? Without explicit, line-by-line instructions. It should be able to, please go to the store and get me the following groceries, that kind of thing. Yeah, this I think will be quite profound, because if you say, what is the economy? It is, at the foundation, it is labor. Yeah, but I think essentially in the future, physical work will be a choice. If you want to do it, you can, but you won't need to do it. Given that the economy at its foundational level is labor, capital equipment is just distilled labor, then is there any actual limit to the economy? Maybe not. Join our team and help build this.